Hello, my name is Sarah Parker, and I am presenting my final project for machine learning. For my final project, I decided to build a melanoma detection model using transfer learning on dermascopic images. So melanoma is the #1 most commonly diagnosed cancer in the United States. And if it's detected early, the survival rate for 5 years is greater than 98%. However, with a late stage diagnosis, that survival rate drops to less than 25%. And this is a huge disparity between the two. Part of what makes melanoma very challenging is that it can be very visually indistinguishable from benign lesions. Even trained dermatologists will disagree on ambiguous dermoscopic presentations. Computer-aided diagnosis systems are powered by deep learning, and they offer a promising supplement to clinical assessment. So for this project, I used the HAM 10,000 dataset, and this comprised of more than 10,015 dermoscopic images. It's about an 8-to-1 class imbalance because you have melanoma, you have nevi, you have actinic keratoses, vascular diseases, and a few others. And so we made this kind of more of a binary issue and reformulated it into either melanoma or non-melanoma. And the non-melanoma cases are obviously going to dominate our data set. And so this makes just naive training likely to produce a classifier that's biased towards the majority class of non-melanomas. So for pre-processing, we split our data into 70% training, 15% validation, and a 15% test. And kind of just to preserve our class ratios. To handle the imbalance of our classes, we used a weighted random sampler, and that oversamples our minority melanoma class without synthesizing new data. We also made sure that we processed the images and did rotations up to 20 degrees, randomly horizontal and vertical flips, did some color jitter, and we resized to 224 by 24 pixels. And this was to the ImageNet normalization. So this exploits our rotational and illumination invariances that are inherent to dermoscopy. Basically, like the lesions aren't always, there is no top and bottom, left to right. They need to be able to be evaluated from left to right, top to bottom, horizontal, and all of the axes. So the architecture that I chose is the EfficientNet BO. It's pre-trained on ImageNet and it has 5.3 million parameters. You can compound the scaling strategy and do a feature extractor in phase 1. We then used a custom classifier head. So we used a dropout of 0.4, a ReLU activation, and a second linear of 256.2. Our binary output was either that the image was melanoma or it was not melanoma. So I used a 2-phase training strategy in phase 1. That was kind of our warm-up. It was epochs 0 through 4. And we kind of did like a frozen backbone, so our feature extractor. It was only the classifier head that was trained. We used an atom optimizer, and we kind of let the head converge before perturbing the backbone. So you can kind of see that 0 to 4 on our diagrams below, where you kind of have that drop off and then it kind of stabilizes. Phase 2 is the fine tuning. So all of our parameters were then unfrozen. So it was full end-to-end fine tuning. Our learning rate was increased, our weight decay was increased. And then every model that produced the best validation accuracy was saved so that we always had like our best model as our checkpoint. So overall, the accuracy was 90.49%, which is fantastic. But the melanoma recall was only 73%. So if you look at our confusion matrix, you'll see that like on our non-melanoma true, it was flagged about 1,238, but that misses about 122 of things that are melanoma, but it thinks was not melanoma. So this is kind of an example. This is our error analysis. So our false negatives, we had 45 missed melanomas. This is the most clinically significant error type because these are images that would not have been flagged as melanoma and would have just continued on down the pipeline as being there. Our false positives, these are the ones that were flagged as being melanoma, but they were not. So essentially, this might end up in an unnecessary referral or further diagnostics, but typically this is more acceptable than a false negative because you're kind of over treating the patient and then finding out that it's actually a negative versus missing a false negative. That patient might not get the referral that they need or further diagnosis, and that's where you can end up in those later stage diagnoses. We used a grad cam model to kind of highlight the areas that were being targeted the most in our model's prediction. And so you can see like in our true positive, it's a heat map image of where it was flagging the most. And then our false negative where it was missing it kind of in those bright red areas as well. And this just helps us, if we were going to continue working on this model, how to fine tune those areas to pick up what's actually being missed. So some of the limitations to this project is the demographic bias. Most of these dermascopic images were collected from European populations, so the model may generalize poorly to patients with darker skin tones. And this is actually very clinically significant for African Americans. We oversimplified it. We collapsed 6 non-melanoma categories, and that could actually contain really useful discriminative information about clinically significant lesion types. So for example, like in an actinic keratoses, that's not considered melanoma, but it is a higher risk for turning into a melanoma. And so those images were just discarded as simply non-melanoma. There was no patient metadata, so we were only looking at the images. There was no access to age or anatomical location, lesion history, prior biopsies. All these are very important when diagnosing melanoma. It's not simply based off the lesion itself. This could be added into a model to provide better precision. There's also limited explainability. Beyond our grad cam visualization, the model lacks kind of that uncertainty quantification that we would need for clinical trust and regulatory compliance, such as why did it miss those lesions? So our key takeaway is that transfer learning via the EfficientNet BO model is viable for dermascopic melanoma classification, but not as a standalone diagnostic tool. It may prove to be a promising first pass filter for dermatologists, but there would still need to be quite a bit more fine tuning to increase that precision. So hypothetically, on those 10,000 images, 1,100 were true melanoma cases. We flagged about 803 with our 73% recall, but that still leaves 300 missed melanomas and 660 false alarms. So there's definitely some improvements that would need to be made before this could be rolled out in an actual clinical feature. Some future directions that this project could go is the focal loss. So finding an alternative imbalance remedy, coming up with some different strategies to handle the fact that we are about 8-to-1 in this data set. Some threshold tuning, so optimizing that precision recall trade-off. Test time augmentation could improve some prediction. Doing some different ensemble models, combining EfficientNet variants could improve it. And then rather than just making it binary, actually increasing that to all 7 of those categories to see if that gives the model better information to flag those melanoma versus the other 6 classifications of the dermascopic agents. So this was my final project. I felt like it was very informative and actually could be used in clinical diagnostic settings in the future. And I think machine learning has a really big role in clinical healthcare. Thank you.